last presentation, sorry, which will be Zhang from Argonne National Lab. And again, this is a more advanced topic on using adjoints in the context of optimization. So.
I'll start from the motivation and background. Then I will go through existing approaches for sensitivity analysis. Then I will introduce adjoint solvers in PETSc. Then I will show you how to use PETSc and tau to solve a dynamic constraint optimization. I will also give you some PETSc tips and advice. Finally, I will conclude my talk with some takeaways. But PDE constraint optimization is an increasingly important problem in DOE applications. In such problems, the objective depends on system states, which can be only obtained by solving a PDE. So for example, the data simulation problem, we have a base simulation, which obviously doesn't match the observation data. So we want to come up with a new initial condition to minimize the discrepancy between the new prediction and the observation data. So for such problems, gradient-based optimization algorithms are usually used. These algorithms require first-order derivatives, sometimes second-order derivatives, to solve these problems efficiently. So this really motivates our interest in sensitivity analysis. Generally speaking, sensitivity analysis can quantify how much model output are affected by changes in the model input. It can be used to identify most influential parameters, to study dynamical systems, and most importantly, to provide a gradient for objective functions. Apart from the applications in dynamic constraint optimization, there are a variety of other applications. The easiest way to compute sensitivity is to use the final difference approximation. It's easy to implement. We all know about that. But it's not efficient for some cases because we only can perturb one parameter at a time for classical final difference method. So if you have many parameters, you end up solving the equation over and over again. A technique called graph coloring can allow you to perturb multiple parameters at the same time, but this doesn't treat the model as a black box anymore. It requires the information about the structure of the gradient vector. And finally, the error of final difference approach highly depends on the runoff error and the truncation error, which makes it difficult to determine an optimal choice for the perturbation value. Another approach is to use automatic differentiation. Automatic differentiation can evaluate the sensitivities for an arbitrary sequence of computer codes. It's a great idea. I like it. A lot of scientific applications would not be possible without AD. But AD suffers from many low-level difficulties, such as the pointer's dynamic memory directives. So sometimes it's just not impossible to fully differentiate a big library code. So while final difference may not work, AD is not an option. What can we do? So our approach is to compute the gradients by differentiating the time-stepping algorithm used for solving the differential equation. Take our favorite backward Euler method, for example. If we differentiate the equation with respect to the parameters of interest, we end up with a forward sensitivity equation, which can be solved together with the original simulation. Another approach is called adjoint method. I'm not going into too much details about the adjoint method. It works like magic. All I want you to know about is this method requires a forward run followed by a backward run, propagating the sensitivity variables from the end of the simulation to the beginning. So one thing to notice is that it requires the information from the forward run. So you see the yn plus 1 here. So this information comes from the forward simulation. Another thing I want you to notice is it solves the transposed system opposed to the original system Fy in the forward simulation. So the fact that the adjoint calculation requires the information from the forward simulation brings up an interesting problem that I will address in a minute. The computational cost of adjoint method is independent of the number of parameters. So this is very favorable for optimization problems that you have many parameters to optimize. Because our approach is associated with the time-stepping algorithms, so it's suitable to be implemented in general-purpose libraries. For example, PETSc. So Barry has already introduced the PETSc in many details. I will not repeat that. Because of the hierarchically organized structure of PETSc, our development can enjoy almost all the benefits from the low-level components of PETSc, with the most important ones being the iterative linear solvers and nonlinear solvers and preconditioners and adaptive time-stepping solvers. So similar functionality is also available in other libraries, such as sundials and neutrinos. This talk will focus on our experiences only in PETSc. The PETSc adjoint solvers have been have been used in many applications, ranging from power grid simulation, Navier-Stokes problems, CFD, and data simulation. So these different applications use very different programming languages. For example, Julia, Python, C++, and C. So it's not a problem if you are a fan of either of these. The PETSc adjoint solver is designed for general purpose solutions. So we want to minimize intrusion. We don't want to change the existing time-stepping solver much. And we want to reuse the functionalities as much as possible. So the essential components in the PETSc adjoint solver include TS trajectory get, which is responsible for checkpointing, TS adjoint event, which is responsible for event detection and handling, and TS adjoint step, which is the adjoint version of the TS step. We also have an adjoint monitor to monitor the adjoint solution. So almost all the components in the existing time-stepping solver have a corresponding component in the adjoint solver, except the TS adapt, which is responsible for time-step adaptivity. So why this component is missing in the adjoint solver? This is because we are doing discrete adjoint. So in the backward run, we follow exactly the same trajectory as the forward simulation. So there's no step size adaptivity in adjoint run. So if you want to compute the sensitivities with respect to initial conditions, you don't need to provide any extra information except the traditional right-hand side function and Jacobian needed by the forward solver. But if you want to compute the sensitivities to parameters, you need to provide additional Jacobian with respect to parameters. So previously, I have mentioned that the adjoint calculation requires the information from the forward run. So ideally, we want to store the solution for all the time steps in the forward run. But in practice, this is sometimes not possible. We are only allowed to store the solution for selective time steps and recompute the missing ones. So this brings up the interesting problem called checkpointing. And this problem has been perfectly solved by an existing library called Revolve. This plot shows an optimal checkpointing schedule generated by Revolve, given 3 allowable checkpoints for 10 time steps. So basically, we need at least 6 extra recomputations, which has been proven to be optimal. So sometimes we want to use disks for checkpointing, even we know that disk I/O could be expensive for best efficiency. So we have been working on multi-level checkpointing schemes that can take advantage of multiple storage media, such as RAM and disk and some other media. To validate the correctness of hand-coded Jacobian and gradients, PETSc and tau, which is a toolkit for optimization, it's shipped together with the PETSc package. So PETSc and tau can test your results against the final difference approximations automatically. Sometimes the final difference approximation may not be reliable, but it can still give you confidence to some extent. So for example, the output in the first box shows that the difference is at the order of 10 to negative 8, which basically tells you that your Jacobian function is reliable. The second box shows the difference between the adjoint gradient and the final difference approximations. You will see that there's a big difference in the result, which tells you that there's definitely something wrong in your adjoint results. And if you take a look at the angle cosine, which is close to 1, which means that the angle is close to 0 degrees. That means this gradient agrees with the true gradient in the descending direction. So I would say this gradient information partially works because you have the right direction, but the wrong magnitude. So usually this indicates a problem in the terminal conditions for the sensitivity variables. So here I want to show you the basic steps you need to take to use PETSc and tau to solve dynamic constraint optimization. The workflow is very straightforward. You start from creating a tau object and set the type to be BLMVM, which is a quasi-Newton algorithm. And this is highly recommended for dynamic constraint optimization. And you can provide an initial guess, which is not required. And you need to provide a function to evaluate the cost function and a function to calculate the gradient. Alternatively, you can combine these two functions into one function and feed it to tau as a bundle. So your simulation code and the adjoint calculation can be encapsulated in this gradient function, my gradient function. So inside this function, you just create a time-stepping object. You set up the options. For example, we set the type to be a Crank-Nicolson here, and we provide the residual function and Jacobian function to solve the time-dependent problem. And we do a forward solve by calling TS-solve, followed by an adjoint solve to get you the gradient information. And notice that the terminal conditions, which are the initial values for the adjoint values, need to be set properly. So this is crucial in practice. So PETSc has some examples that you can follow to build your own applications. So these examples range from ODE, DAE, and time-dependent PDEs. I will show you the highlighted examples in a hands-on session. In addition, I'll give you some tips and advice, which I think is very important based on our experiences in the past few years. So PETSc can approximate the Jacobian automatically using coloring. It's particularly convenient if you're using DMDA for data management. And most of the difficulties stem from the mistakes in the hand-coded Jacobian. So make sure to validate the Jacobian carefully. For best accuracy, we suggest you to try direct solvers such as SuperLU and MUMS. And we have tons of monitor options that allows you to monitor the solver behavior and profile the performance. If you're running your code on Intel's nice nanning processors, we have a special option which allows you to do the computation using the fast memory and checkpointing using the relatively slow memory on kernel. which is still way faster than using disk for checkpointing. So lastly, check the user manual and the website for more information, and ask questions on the mailing list. We answer every question from the user. To conclude, I have introduced the Adjoint as an enabling technology for optimization. The efficiency of our Adjoint solver comes from the highly developed PETSc infrastructure. PETSc requires minimal user input and reuses the information, the user-provided information as much as possible. The full software stack can help you rapidly develop your own parallel application code. And PETSc provides advanced checkpointing and validation so that you don't have to write your own code for these essential components. Thank you for your attention. Any questions before I get to the hands-on session? I really encourage you to try to run these examples because they're very simple to run. It doesn't require any, any files. It's just 3 simple binaries. So the first example is an ODE constraint optimization problem. It can be solved using a combination of PETSc components such as tau, TS event, TS adjoint, and TS. TS stands for time stepping. So the objective is to maximize the mechanical power input subject to the generator's swing equations and a constraint on the maximum rotor angle deviation. It's not important to know the physical meanings of this problem. We are more interested in the mathematical abstraction. So the objective contains an integral term over the time interval, the equation being solved. And there's a disturbance applied to this system at a specified time 0.1 and cleared at 0.2. I want you to look into the source code. So the most important function in this source file is the form function gradient. Inside this function, we calculate the objective function and the gradient information. So we created a TS object, and we provide a function to evaluate the residual and a function to evaluate the Jacobian. And in addition, we provide a function to calculate the integrand in the objective function. Then we do a TS solve to solve the forward equation. And an adjoint solve to get a gradient. So you can use the minus help to get the command line options available for this particular example. So what it prints out is not all the options in the library. It's just the command line options that you can use for this particular example. And we can do a graph to get the options related to tau only. So if we run it with tau monitor and tau view, you can see the progress of the optimization solver. The optimization algorithm converges in 8 iterations. The second example is a hybrid dynamical system. The right-hand side of this hybrid system can change from one form to the other form depending on the states. So if you take a look at the trajectory of this system is bouncing between two lines, approaching the equilibrium point, which is the origin. So in PETSc, we can draw the solution by using TS monitor, draw a solution face. Then we specify the range of the solution. So the first run will give you a plot which should look similar to the phase plot here. In the second run, you can try to use the TS monitors to monitor the progress of the time-stepping solver. And you can add TS event monitors to see how PETSc handles the event mechanism. And TS adjoint monitor will show you the progress of the adjoint solver. You will see the step size being negative during the adjoint run, because the adjoint solver is propagating the adjoint solution from the end of your simulation to the beginning. So you will see a negative step size printed out. And the last example is a diffusion reaction problem. It's a time-dependent PDE on a two-dimensional rectangular grid. The adjoint solution in this example corresponds to the sensitivities of one component in the final solution with respect to the initial condition. I will try to run it to see if this one works. Okay, good, it works. So let's run it again. So this shows the solution of this problem. For the second run, I will show you how the checkpointing schedule works. Since I'm running out of time, I will not run it for you. So you can try it yourself. Just copy these commands. And in output, you will see how PETSc handles the checkpointing. When you specify there are only 3 available checkpoints in RAM. We can also use this command, this option, to specify 2 additional slots for disk checkpoints and to find out what happens yourself. And lastly, you can try the implicit time integration method as well, and use the log view to print a summary of the logging. So in the log, you will see how much time each component takes. Then you can find out the answer for these questions. Where is the majority of the CPU time spent? Usually, the majority of the CPU time is spent on kernels such as matmult, matrix vector product, or vec m dot, which computes multiple dot products. And you can also compare the computational cost for an adjoint step and think about how we can improve performance. So basically, most of the techniques you have learned today can be used here. For example, you can try to use better time-stepping algorithm. You can try better preconditioner or better linear solvers and so forth. Thank you.